Okay, so today we just want to review some of our polynomial technology, or terminology, using technology. All right, but here, it's just, this is again the generic thing. It looks really intimidating, but the big thing to realize is a sub n is just, the a's are all just going to be numbers, and these are just subscripts. Right? It's just saying, this way you can use the same letter 1,000 times if you need to. You're never going to run out of letters. Like compared to the quadratic formula where you use A, B, and C. You know there's only 3. So what we do is we say that whatever subscript is here on this a will also match the power here. So if this is an x cubed, this would be a sub 3. Right? If this was x to the 10th, this would be a sub 10, is how we refer to that. You'll notice the powers decrease by 1 each time. So if this is a power, this is 1 less. We keep decreasing until we get second power, first power, and then no power at all. And the coefficients do the same way there. So the biggest power you see is going to be the degree of the polynomial. So this polynomial would be degree n. Right? Just that's the biggest power. Right? If the biggest power is an 8, it's an 8th degree polynomial. Biggest power is a 3, it's a cubic or a 3rd degree polynomial. The numbers a sub 0, a sub 1, a sub 2, etc., on up to a sub n are called the coefficients of the polynomial. Right, and that's just the number parts in front of the x parts. Right? So when you have a polynomial, you should never have all these a's in there. You're going to have numbers for those. Those are called the coefficients. A sub 0 has a special name. It's called the constant term. Right? It's just going to be a single number and have no x on it. By looking at specific parts of kind of the generic polynomial, we'll be able to describe things like what its end behavior is. Maybe, you know, if both ends go up or both go down or one up, all these different things we can describe. Or we have some different points. The leading coefficient is the coefficient to the highest power. And that would be a sub n, right? So that's the leading coefficient. It's the highest power. The last thing that we'll see is called the leading term. And that's a sub n x to the n. So the leading term is the leading coefficient and the highest power part. I kind of break it up there. We have some different names for some different pieces. So I think now as we look at some of these in this next table, it's going to make more sense kind of where these go. So let's go ahead and take a look at that table. So as we look at these, we have this next table here on our worksheet. The first one is just a constant function. This is just f of x equals 4. That's just a horizontal line, correct? That's really, technically it's a polynomial. It's just really kind of a boring one. So the leading coefficient, I mean, I guess we could say that's 4. It's kind of a weird thing, but it's the biggest power is x to the 0 power. Right? So this one, it is important. This would be a degree 0 polynomial. If it's degree 0, it's going to be a horizontal line. Right? If it's degree 1, it's going to be an oblique line. We actually have a slope. The leading term would again just be 4. The constant term would again just be 4. So that was definitely a weird one to get started with, but hopefully all those facts make sense there. So as we look at this second one here, p of x equals negative 5x plus 6. Right? So again, we have a line here. This time it has a slope of negative 5. The leading coefficient would be the number in front of the biggest power. So the biggest power is x. So the leading coefficient is negative 5. Degree, right? The biggest power we see of x is the first degree. So it's degree 1. The leading term, again, that makes up that whole first piece. So it would be negative 5x. And then the constant term would just be the constant, which would be 6. So why don't you take a second here, try to figure out what the rest of these would be. The one piece of advice, it didn't come up here, but we have to be very careful about this, is you always want to write these in standard form, right? You always want to start from the highest degree and work your way down. It'll make it a lot easier to figure out the answers to some of these questions. If they're all jumbled, it can be really confusing. So, okay, so for the next one here, we have g of x, which is 6x to the 8th minus 9x cubed plus x squared. So our leading coefficient, really, it's probably easiest to find the leading term first, right? Once you know the leading term, it answers these two questions. So here, the leading term would be a 6x to the 8th. So then the leading coefficient would be the 6. The degree would be 8. And then the constant term, now that's the constant, so constant means no variable. It's a little tricky here. There's, like here, it's obvious it's a -3, I hope. But here there's nothing there, so our constant term would actually be 0. Now, what we'll find is this constant term is going to show us where the y-intercept is at every time for the graph. So it's really just a kind of a free point that you don't even have to plug anything in for. Just identify the constant term. The next one here, q of x, we see our leading term is -4x to the 6th. Again, I did check to make sure they were in order here. So -4x to the 6th. The leading coefficient would be -4, and it is important that it's negative number. The degree would be 6, and then the constant term would be -3. And then lastly here, we have this. And again, I think that you talked about or looked at some of these words, but this would be a binomial, right? There's two terms, a trinomial. This would be a monomial. These are some words that we've seen here. So the leading term here is -19x to the 5th. So that'd be -19. The degree would be 5. And again, there our constant term would be 0. Did we get those? Okay. So the next part asks us here to write a polynomial function of degree 8 with 4 terms, a leading coefficient of -6, and a constant term of 11. That's a lot of stuff, right? Did anybody have one that they could give us? Did you do that one? Yeah.
I have -6x to the 8th plus 4x squared plus 2x plus 11.
So what do we think? Is that degree 8? It's got 4 terms. It is degree 8. Leading coefficient of -6. Constant term of 11. Yeah. Thank you. Did we get something like that? Now the things you have to have, I think, are you have to have that, and you have to have that, and you have to have 4 terms. But you get dealer's choice for the middle ones. Do whatever you want there. Monomial function of degree 1. Yes? X. I like it. It's efficient, right? You could give them names. You could say f of x equals or p of x equals. Yeah. Just anything that has an x in it. Can be any coefficient you want. It's all good. Lastly, a polynomial using the following coefficients: 3, -7, 2, 8, -4, and 6. Did you guys do what I did? I just decreased. I was like, okay, 0, 1, 2, 3, 4, 5. Okay, so I have 3x to the 5th minus 7x to the 4th plus 2x cubed plus 8x minus 4x all squared minus 4x plus 6. That would work. There are lots of other ways it would work too. Sure. You're just going to have 6 terms is kind of the thing you want to do. You could do any powers you wanted there. They're all great. Okay, so here for our first ones, and again, with polynomials, one of the first things you're going to do to sketch them is find the x-intercepts. Right? It's huge, hugely important thing. So we just wanted to review some skills. Remember though, when you are finding x-intercepts, you're going to take y or f of x or h of x, and you're going to set it equal to 0 and solve. X-intercepts though are going to be ordered pairs, so it's probably a good idea that we write our answers as ordered pairs. And also, whenever we're talking about x-intercepts, we don't want to consider imaginary numbers because x-intercepts refer to the x-axis of a graph, right? And the x-axis only has real numbers on it. So while we will talk about complex numbers, in terms of graphing polynomials, they don't mean anything. They're just kind of these weird little guys. So we need to go ahead and factor this, I think, is the way to do this. If we want to split the middle, we need two numbers that multiply to be -6 and add to be 1, which would be 3 and -2. So that's 2x squared plus 3x minus 2x minus 3. And then we're going to group it, hopefully. So this first pair, we could take out an x. We're left with 2x plus 3. The second pair, we'll take out a -1, and we're still left with 2x plus 3. So then we get x minus 1, 2x plus 3. And again, this is a case where we're using factoring to solve, so we're not done. We're going to set each factor equal to 0. And you can only do this when it's equal to 0 as a product. If it's anything different, it doesn't work. So x minus 1 equals 0. 2x plus 3 equals 0. So we get x equals 1 or x equals -3/2. That means that our x-intercepts will be at 1, 0 and -3/2, 0. So again, it's nice to actually write those out as points because they are x-intercepts. This will help too if you're someone who maybe you miss points on quizzes or tests sometimes because you're asked to factor, right? And then you end up solving them and you're not supposed to, or different things. We just really want to make sure that factoring is a tool that we're using to find the x-intercepts. Like the x-intercept part's a little bit further along there. This next one here, g of x, we have 4 terms. So if we think back to our factoring techniques we talked about earlier this year, we know that we do look for a greatest common factor first, but we don't see one. So then we're going to try to group it. At this point, that's all we can do with this polynomial. Now, once we start doing synthetic division, we'll have more tools that we can do this. So 0 equals x cubed plus 7x squared plus 2x plus 14. Factor by grouping, so x squared, x plus 7, and then 2, x plus 7. So since they match, that's what we wanted, right? We know that we can write this in a factored form, x squared plus 2, x plus 7. Set each factor equal to 0. Well, we get x equals -7, but this one, you see we're not going to get real solutions here. You're going to get x squared equals -2. Now, that would still be a complex 0 of the function, right? It still makes it equal to 0. Doesn't mean anything with our graph because we're graph over the real numbers. So that's going to be, we don't need to do anything there. So for the x-intercept would be at -7, 0. Okay, number 3 is a nice one because I would hope that you tried to factor it and then you said, hey, what two numbers multiply to be 2 and add to be 8? Then you quickly decided that there are not two numbers that we know that do that. So we're going to have to use the quadratic formula. We're still solving those. 0 equals 2x squared plus 8x plus 1. Don't forget the quadratic formula needed a 0 equals. That's part of the thing. So we get, if you don't know it, you really got to learn it soon. I like to just write it out once or twice every time I use it. That way it kind of sticks with me. You know? So here we get -8 plus or minus the square root of 64 minus 4 times 2 times 1 over 2 times 2. So -8 plus or minus radical 56 over 4. Kind of depends what we're doing here. If we're looking for x-intercepts, we're probably going to want to get a decimal approximation because I have no idea where that fits on a number line. Like that's just a pretty bizarre number. If we actually had to solve it exactly, though, we would need to simplify it a bit. That's radical 4 times radical 14. That gives us 2 radical 14 over 4. All right, and if we look at this now, we know that we can factor a 2 out of the top and cancel on bottom. And then we get negative 4 plus or minus radical 14 all over 2. So that would be the exact solution, right? Simplified, all that good stuff. But let's see what it would actually be with the actual x-intercepts we would want to draw on the graph would be at negative 0.1290 and negative 3.8710. These would actually be our x-intercepts. Now, if you knew you were just finding x-intercepts, you don't need to do all this part, right? You could have just stopped and typed this in your calculator. Or better yet, if you have a program for the quadratic formula, you could have typed your program in, right? Which I have one, but my link cable's broken, right? Give it to you. Just find one online, just type it in. They're pretty, it's about 10 lines of code. Okay, last thing for today is when we have a multiple zero, or what that would be is a repeated factor, and we have a case of what's called multiplicities. So for example, if we have the polynomial p of x equals x squared, x plus 1, x plus 3 cubed, right? So this is a polynomial. This is in factored form, correct? So meaning we do not want to we don't expand this, it's already factored. But what this is going to give us here is we see that this x tells us that there's a 0 at the origin, correct? At 0. But it's squared. That squared is called the multiplicity of that 0, or the multiplicity of that factor. Here we have x plus 3 as a factor. It's cubed. So we'd say its multiplicity is 3. You might be like, well, great, more words that don't mean anything to me. But it actually gives you a really nice piece of the graph here. So as we look at this, maybe to kind of make a table, if we look at each of the individual factors, so here I had the factor x squared, correct? Well, that tells me there is an x-intercept at 0, 0. Okay. And this also tells me, because it's squared, that it has a multiplicity of 2. And what that means is one of two things is going to happen there. This is where maybe you remember that things bounce sometimes. They bounce off a certain 0. So on this case, for this graph, here's my 0. It's either going to come down and touch it and go back up, or it's going to come up, touch that point, and go back down. These look like parabolas, right? Multiplicity of 2, it looks like parabolas right near the 0. It'll come down and touch it and go back up, or it'll come up and touch it and go back down. If we look at this factor x plus 1, that would give us an x-intercept at negative 1, 0. It doesn't have a multiplicity. It's just a typical 0, correct? So what do you think the line's going to do when it hits there? Just goes right through like normal, right? So it's either going to be like that, or like that, right? Just something, just going to cross right through it. What you'd expect. Okay. Our last case is this x plus 3 cubed. So that would give us a 0 at negative 3, 0. And that has a multiplicity of 3. So you might notice a multiplicity of 2 looked like a parabola in that little region, correct? Multiplicity of 1, or no multiplicity, just looked like a line at that area. What do you think a cube's going to look like? A cubic, yeah. So this would either look like, so we're out here, it would look like that, or it'll look like a cubic, right? Like your John Travolta graph, right? Like, that's what it's going to look like there. So if you have a multiplicity, or any odd multiplicity, 3, 5, 7, will look like one of these two. Any even, 2, 4, 6, will look like a parabola. Yeah?
So the multiplicity is just whatever the degree is?
Yep, it's whatever the degree of that factor is. But notice that before we can do any of that, we have to have it all factored. But yeah, once it's factored, If you get a squared, you know it's multiplicity of 2. Or if you get a cubed, you know it's multiplicity of 3. So kind of what we're going to do is collect a bunch of facts about polynomials here the next day or two, and then look at how to get them on a graph. Like take all these facts, how we can make a decent sketch of what we're looking at here. Okay. So for tonight, I would recommend that you take a look at, and this is linked on the agenda, page 188, 29 through 42. All the answers are listed afterwards. But go ahead and look at those. Make sure that you are feeling good with this stuff, and then we'll add on from here.